friends, in this video we are going to study about the Kelvin double bridge method, which is used for the measurement of low resistances. Low resistances means those resistances which are having the value from 0 ohm to 1 ohm. So let us start with our topic. The Kelvin's double bridge method, it is the most popular method which is used for measuring the low resistances very accurately. This bridge, that is Kelvin double bridge, it is a modification of the Wheatstone bridge. Wheatstone bridge, we are very much aware about it, that this Wheatstone bridge, it consists of 4 arms, and in the 4 arms we have 4 resistances, and the bridge, that is Wheatstone bridge, it is said to be balanced when the ratio of the resistances in one arm is equal to the ratio of the resistances in the other arm. So if we draw the circuit for the Wheatstone bridge, it will be like these are the 4 ratio arm A, B, C, D. Okay, we have the 4 resistances P, Q, R, N, S. Okay, so this Wheatstone bridge is balanced, that is the galvanometer, it will show the null deflection. That means that will be 0 when no current is flowing through this arm BD, and that will happen when P by Q is equals to R by S. Okay, so this is the Wheatstone bridge. Now Kelvin double bridge, it is a modification of the Wheatstone bridge, because Wheatstone bridge, it can measure the resistances which are from few ohms to several mega ohms. But if we want to measure the resistances which are very low, that is under 1 ohm value, then we will use the Kelvin double bridge, and for that we have to do some modifications in this Wheatstone bridge. So before starting with the Kelvin double bridge, let us see the principle due to which we have to use this Kelvin double bridge method. Okay. Now for that, suppose that this P, Q, these are the known resistances in the Wheatstone bridge, R is the unknown resistance, and S is the standard resistance. Now we are calculating this unknown resistance R by this formula, that is P by Q into S. So we can use this Wheatstone bridge also for the measurement of resistance, but in that case, when we are implementing this Wheatstone bridge in the laboratory, then P, Q resistances, all these resistances are connected to each other through the connecting leads. Okay, so this unknown resistance, it is connected to the standard resistance through the connecting leads, and that connecting lead will also have some resistance. So if we want to measure the resistance of that connecting lead, we can use the Kelvin double bridge, because the resistance of connecting lead will be very small. Okay, so here in this modification, what we are doing, in between R and S, we are considering a connecting lead, and we want to measure the resistance of that connecting lead. So let's draw the circuit here. Okay, so this modification we have done from the Wheatstone bridge in the Kelvin double bridge. Now in this Kelvin bridge, what we see that here we are having a connecting lead which is connecting the unknown resistance R to the standard resistance. Now let us suppose that this connecting lead is having a resistance value which is R. Okay, so R is the resistance of this connecting lead. Now this galvanometer, it can be connected to the point M also and to the point N also. When this galvanometer is connected at point M, then this resistance of the connecting lead is added to the standard resistance. And when this galvanometer is connected to point N, then this resistance R of the connecting lead is added to the unknown resistance. So there are two connections for the galvanometer, either at point M or either at point N. So when the connection is at point M, then the resistance of the connecting lead, that is a small r, it is added to the standard resistance. So S will become S plus R. Okay, so in the ratio of what we have studied in the Wheatstone bridge, that is R equals to P by QS. So this R will be equal to P upon Q, and this S is replaced by S plus R. Okay, so here we will get the value of the unknown resistance as greater than the actual value. Now when the galvanometer is connected at point N, then this resistance of the connecting lead is added to the unknown resistance. So R will become R plus small r. So here again the ratio will become R plus small r equals to P by Q S. Okay, so in both the cases, if you will see, the value of the resistance which we are getting, it is not the true value of the resistance. At point M, the value will be lower than the actual value, and at point N, the value will be greater than the actual value. Okay, so here in the case of point M, we are getting low result, and at point N, we are getting high result. Okay, so this connecting lead, it is having an effect on those values. Now here, suppose that instead of making the galvanometer connections at point M and N, we are making the galvanometer connection at a point D, which is intermediate between point M and N, such that the resistance, that is R, the resistance of the connecting lead, it is divided into two parts, R1 and R2, such that the ratio of R1 upon R2 is equal to the ratio of P by Q. So we are making the connection of the galvanometer G at an intermediate point D, which is dividing the resistance of the connecting lead into two parts, R1 and R2, such that the ratio of R1 and R2 is equal to the ratio of P by Q. Okay, so R is divided into R1 and R2. R1 upon R2 is equal to P upon Q. So when the connection of the galvanometer, it is made at point D such that we are having this ratio, then no error will occur in the measurement. Means this low result and high result conditions, they will be eliminated. So how? Let's see. Now when the connection is at point D, then in this ratio P upon Q equals to R by S. In R we are adding this resistance R1, and in this standard resistance S we are adding this small resistance R2. So this ratio will be changed, that is P upon Q equals to R by S, that will be changed. In R we are adding small R1 and P upon Q. Here in S we are adding the resistance R2. But we know that this R1 upon R2 is equal to P by Q. Okay, so from this formula we can get the value of R1 upon R1 plus R2. It will be equal to P upon P plus Q. What we have done? We have R1 upon R2 plus 1 and P upon Q plus 1. We are adding 1 on both the sides. We will get R1 plus R2 upon R2 equals to P upon Q, P plus Q upon Q. So from this, if we reverse this expression, we will get R2 upon R1 plus R2 equals to Q upon P plus Q. Similarly, if we take the reverse ratio, that is R2 upon R1 equals to Q by P, and then adding 1 and 1, we will get the ratio R1 upon R1 plus R2 equals to P upon P plus Q. So we are getting these two ratios from this expression. So R1 upon R1 plus R2 equals to P upon P plus Q. So from this expression, we will get the value of R1 as P upon P plus Q into R1 plus R2. And we know that R1 plus R2, it is equal to the complete resistance of the connecting lead. R1 plus R2 is equal to R. Okay, so here we can replace this R1 plus R2 by R. So this is the value of R1. Now from this expression, that is R2 upon R1 plus R2 equals to Q upon P plus Q, we will get the value of R2 as Q upon P plus Q multiplied with R1 plus R2. Again we are getting R2 as Q upon P plus Q. R1 plus R2 is what? Again R. So this is the value of R2. So from this expression, R1 upon R2 equals to P by Q, we can get the value of R1 also, and we can get the value of R2 also. Now, after getting these two values, let's put this value in this expression. R plus small r1 equals to P by Q S plus R2. So we will get R plus small r1 is what? P upon P plus QR. And here we have P upon Q S plus R2 is what? This value Q upon P plus Q into R. Now when we solve this, what we will get? P upon P plus Q into R. And here if we multiply this, Q and Q will be cancelled. Again we are going to get P upon P plus Q into R. So that will be cancelled. Q and Q are cancelled. Again we are getting PR upon P plus Q. Here also PR upon P plus Q. So they will be cancelled. So we are getting the last expression as R equals to P upon Q into S. So from this expression, we can conclude that if we are making the galvanometer connections in the bridge at a point D such that the ratio of R1 upon R2 is equals to P upon Q, then the connection or the resistance of this connecting lead will have no effect on the circuit. Okay, because we are in the last we are getting the same expression as that we are getting in the Wheatstone bridge. But practically this type of connection is impossible because we are not able to get this point D correctly such that the ratio is equal. So instead of doing this or searching for this intermediate point D, we are making a modification in this bridge, in this Wheatstone bridge, and that modification is called the Kelvin double bridge. So in Kelvin double bridge, there is a simple modification. Instead of this connecting lead, we are using another set of ratio arms, that is, instead of P by Q, we are also using another set which is small p by Q, such that this resistance we can measure easily, okay, such that the ratio of this P upon Q and the ratio of that small p upon Q, that is equal. Okay, so let us study the Kelvin double bridge method. So because through this expression you get to know that why we are doing the modification in Wheatstone bridge, what is the requirement for this modification. Now in the Kelvin double bridge, we are having a second set of ratio arms, so that is why its name is double bridge. Okay, and in this Kelvin is the name of the scientist who developed this bridge, and double bridge because here we are having a second set of ratio arms. So if we see the construction of this bridge, it will have two sets. First set of ratio arm will be P upon Q, P and Q, and second set of ratio arm will be small p and small q. Okay, and the galvanometer, it is connected between the two arms, that is P upon Q and small p upon Q. Let's see the circuit for this Kelvin double bridge. So this is the circuit diagram for the Kelvin double bridge. In this bridge, you can see there are two ratio arms. One set of ratio arm is P upon Q and the other set of ratio arm is small p upon small q. And in between these two arms, the galvanometer is connected. Now R is the unknown resistance, which we that is the unknown resistance, and S is the standard resistance. So P, Q, R and S are just like the Wheatstone bridge. Now in the modification we studied that we are connecting the galvanometer at an intermediate point such that P upon Q is equals to capital P upon Q. The ratio is same. Now here small r, it is the resistance of the connecting lead which is connecting this unknown resistance with the standard resistance. And here we know the value of R and we want to calculate the value of this connecting lead. Okay, so this is the Kelvin double bridge. Now the working principle for this bridge is just like same as the Wheatstone bridge. We want to find a point where the galvanometer gives us a null deflection. So in the Wheatstone bridge, when we studied that the bridge will be balanced when the galvanometer gives us no deflection. When the galvanometer gives us no deflection, when there is no current flowing through the galvanometer, that means the voltage drop across the point EAB. AB is equal to the voltage drop across EAMD. Okay, then only the galvanometer will give us null deflection. So we are going to equate the voltage drop across AB points, that is EAB, and the voltage drop across EAMD. Okay. So EAB should be equal to EAMD. Then only this galvanometer will give us the null deflection, and the ratio of small p by q will be equal to capital P by Q. Now let's get the derivation for this Kelvin double bridge. Now in the Kelvin double bridge, here you can see we are just simplifying this part. Okay, if we draw a simple circuit for this part, then across EA means across the point A and C, what is the equivalent resistance? Okay, this R will be connected to P and Q. P and Q are in series with each other. Then in parallel to that, we are having this resistance R, that is resistance of the connecting lead, and then we are having the standard resistance. So if we draw the diagram for the resistance in between the point A and C, it will be like so this is point A, this is point C. In between A and M, we are having the resistance R. So this is R, this is point M. Between M and N, we are having P and Q, which are in series, and in parallel, we are having R. So this is P, this is Q, this is R, this is the point N, and this was the middle point D. So when the galvanometer is showing null deflection, it means this no current is flowing through this. So this circuit or this line can be connected as a short circuit line. Okay, so here we are having the point D, then N is there, and after that we are having the standard resistance N, and then the C point. So this is the resistance in between. Now if we calculate the voltage drop, that because we practically what we have to find, EAB equals to EAMD. We know this thing. Now we have to calculate the value of this EAB, and we want to find out the expression for the resistance. Now EAB is equal to P upon P plus Q into EAC. EAB will be equals to P upon P plus Q and the total voltage drop, that is EAC. Because when we want to find out the voltage drop across one arm, what we have to do, total voltage divided by the resistance, that is P upon the total resistance is P plus Q. Across the points EAC we want to find out. So total voltage is what? EAC. Then we have to give the resistance, that is resistance across the point is P in divided by the total resistance. P and Q are in series with each other. So we have written the expression for EAB. Okay. Now we have to find out EAC. So EAC is what? This is the voltage drop across this point. So what we will do? Complete voltage divided by the resistance, or we can say V is equals to IR. So we know the value of the current. Value of the current is I, and we can write the equivalent resistance. Then we can get EAC. So EAC will be equal to I, that is the current, into the equivalent resistance between the point AC. So what is the equivalent resistance? R plus S plus this parallel combination. So R plus S plus P plus Q into R upon P plus Q plus R. Because P plus Q, they are in series with each other, and then it is in parallel with the resistance R. So we will get the resistance P plus Q into R upon P plus Q plus R. And R and S are in series with each other. So this is the equivalent resistance between the point A and C, and this is the total current. Now, for in this value, we are putting the value of this EAC in this expression for EAB. P upon P plus Q into this I, and then this expression R plus S plus. So this is the voltage drop across the points A and B. So in this figure, if we see A, B, we have calculated this voltage drop. Now this voltage drop will be equal to the voltage drop across A, M, D. Then only the galvanometer will show the null deflection. Okay. So now we will calculate E, A, M, D. Now EAMD will be equal to the current into the equivalent resistance. So current will be the I, and equivalent resistance will be R plus P upon P plus Q, and then that is we are going to add this resistance, the voltage drop across this resistance, plus the MD, that is EAMD will be equal to EAM plus EMD. Okay, so this is the I into R. Okay, same current is flowing through this resistance, so P upon the P plus Q, that will be the resistance, and then multiplied with the equivalent resistance. Okay, so EAMD will be equal to I R plus P upon P plus Q So EAMD, we have divided it. We have added two parts in it. EAM plus EMD. EAM is the voltage drop across the resistance R. So I multiplied with R. We have written it here. I we have taken as common. So I into R will be EAM. Then EMD will be what? The voltage drop across this P resistance. So what we calculate? We know the total voltage drop. Okay, that means the current into the equivalent resistance we are writing. So equivalent resistance is what? P upon P plus Q, and this is the equivalent resistance. So we have written these two, we have combined these two voltages, and this is the EAMD. Now let's simplify this. P plus Q, they will be cancelled out. So EAMD is equal to I R plus PR upon P plus Q plus R. So this what we have obtained, EAMD. We have already obtained EAB. Now what the Wheatstone-Bridge principle says, that this galvanometer deflection will be null when the voltage drops across the two arms is equal. That is EAB is equal to EAMD. So we have the values of both the voltages, so we are going to equate them. So we will put the values of EAB and EAMD and then going to equate it. EAB is equal to, from this formula, we can get its value. We will write it here, P upon P plus Q into I R plus S plus this is the value of EAB. We are going to equate with EAMD. Now in these two equations we have this I as common, so we are going to cancel it out. So we are left with P upon P plus Q and this expression, and on the right hand side we are left with R plus PR upon P plus Q plus R. Let us simplify this. Now on both sides we have the expression for this R. Okay, so what we will do, we are going to cross multiply this P upon P plus Q. We will send it on the right hand side. So when we will send it on right hand side, it will become P plus Q upon P. Okay. Then multiply it inside the bracket. What we will get, R into P plus Q upon P. So this is the expression for R, and here we are having R also. So we are going to bring that on the left hand side. First write it in some simplified form. We will multiply it inside. So what we will get, P plus Q upon P plus this PR upon P plus Q plus R into P plus Q upon P. We have multiplied it inside the bracket. Now this is the expression for R and this is also the expression for R. So we will bring the expressions in terms of R or the coefficients of R on the left hand side and all the other terms on the right hand side. Here if we take R as common, so 1 is left, then minus this P plus Q upon P, we are bringing it on the left hand side, so plus will become minus on this side and we are left with P plus Q upon P. So these are the terms which are having R in them. Then all the terms on the right hand side, so here we will have this S, when it come on the right hand side, it will become minus. So minus S minus okay. Now let's further simplify it. When we do this subtraction, if we take LCM, then P minus P plus minus Q upon P, it will be P as an LCM, P minus Q. This will be like this. So P and P will be cancelled and we are left with R minus Q upon P. Now here if we do the subtraction, we have P upon P plus Q plus R. Okay, now if we take it as common, like from this and this term, we can take P R upon P plus Q plus R as common. Here we are having P plus Q upon P, and here if we take if we multiply this is minus PR upon P plus Q plus R and minus QR upon P plus Q plus R. So we can take common. So here we are left with minus 1. And what the terms we are left with? Minus S and minus of QR upon P plus Q plus R. What we have done, we have multiplied this R inside, so we will get minus PR and minus QR. So minus PR, and this is also PR upon P plus Q plus R, we have taken common here. So we are P plus Q upon P, and here minus 1 is left. Again we are having minus QR, so we have written as it is. Okay. Now let's do subtraction here also. So this will be P plus Q minus P upon P. Again P and P will be cancelled. We are left with only Q upon P. So let's simplify it further. We are having R into minus Q upon P equals to PR upon P plus Q plus R. And inside we are left with Q upon P minus S minus QR upon P plus Q plus R. Now if we take minus sign common from both the sides, then we will get, here we will have minus sign, this will become minus, this will become plus and plus. Okay, so minus and minus signs, they will be cancelled out. Okay, and then Q upon P, we are going to bring it on the right hand side. So we will get R equal to, this become minus PR upon P plus Q plus R. Here we are having Q by P. When we are bringing this on right hand side, it will become P upon Q. So P upon Q and Q upon P, they will be cancelled. Next term we are having, this will become plus. So plus this P upon Q and then this S. This also become plus sign. So plus QR upon P plus Q plus R and multiplying this with P by Q. So what we have done, we have taken the minus sign common. So minus minus will be cancelled on the left hand side, on the right hand side, and this Q upon P we have bring it on the right hand side. So it will become P by Q. So P by Q, P by Q, P by Q, multiplying it with all the three terms. In this term it will be cancelled with this Q by P ratio. Here we are having P by Q. In this term also we have P by Q. Now again further simplify it. If we see, here we are having minus PR and here we are having QR. So we can take common from these two terms. Okay, so taking common we will get, this is as it is P upon Q into S. From these two terms we will have plus, multiply it inside PQR upon Q P plus Q plus R. Writing this on this side, minus PR upon P plus Q plus R. Now let's take common. We are taking QR as common. So from the first term we are left with capital P upon Q, and from the second term, because it is not having Q here, we have taken Q common, so we have to divide it with Q. So we will get P upon Q. Okay. So this is the expression, or this is the final expression which we are getting for the Kelvin double bridge. This expression we have got when we have equated the two voltages EAB and EAMD. Here we have equated the two voltages EAB is equal to EAMB. Individually we have got both the values and then we equated them and then simplified it to get this expression. Now in this expression, if you compare it with the expression for the Wheatstone bridge, for Wheatstone bridge we have R equals to P upon Q into S. So this is present, but this second term is the additional term in the Kelvin double bridge. Now if the value of the P upon Q is equal to the ratio of small p upon Q, which is the condition for the Kelvin double bridge, then this difference will become 0 and this ratio is what we get from the Wheatstone bridge. So if the ratio of P upon Q is equals to small p upon Q, then this expression is reduced to R equals to P by Q S. Okay. Now in the Kelvin double bridge, in the starting we have made the assumption that we are choosing this second set of ratio arms such that this ratio is equal. Okay, so from this expression what we are getting, that the resistance of this connecting lead will have no effect in the circuit if we have kept this ratio as equal. Okay, now the usual expression or the usual equation, actual equation for the Kelvin double bridge is this. Now when these two ratios are not equal, then we can calculate the error in the measurement of the resistance by using this expression only. Here the ratios are not equal, so this is the additional error or the additional value of the resistance which we are getting. Okay, so we can get the error by calculating the difference between the measured value, which is this, minus the actual value of the unknown resistance. So this was the Kelvin double bridge, which is used for the measurement of low resistances, that like for example the measurement of the resistance of the connecting lead between the unknown resistance and the standard resistance. Here in the Kelvin double bridge, because there are two sets of ratio arms, so that is why its name is double bridge. And here we have the R as the resistance of the connecting lead which we want to measure. So I hope that this topic, measurement of low resistance using the Kelvin double bridge method, is clear to you. Thank you.